Can you guys hear me? Raise your hand if you can hear me. Okay. Great. Okay, thanks for the introduction, Andy. So I am here to give a 1 hour, for now, crash course in a subject that I love enough to spend many more years of my life doing it in startup form. So machine learning. Let's start with the basics. What is machine learning? It means a variety of different things to a variety of different people, so I'd like us to at least standardize on some sort of definition for today. And I would say machine learning exists at the intersection of computer science and statistics. So you can see it through a couple of different lenses. Through the lens of statistics, it's a subfield of statistics that happens to care a bit more than classical work in statistics about. So machine learning tends to care more about computation, unsurprisingly, as well as empirical evaluation. Viewed from the lens of computer science, I would say it's a branch of computer science that focuses on algorithms whose performance improves as they're exposed to more data. Okay, so we tend to draw on a variety of different fields beyond these two as well, including optimization, information theory, and others. But we do sit firmly at this intersection. The term data science is used a great deal these days. To put that in context, I would say that machine learning as a field provides tools in the forms of algorithms that are in turn used by data scientists to gain insight from data. So, machine learning at this point basically touches all of us every day, right? Probably don't have to convince most of you about why it's pretty interesting. But every time you use your spam filter, every time you do a search on Google, every time you see an advertisement, every time you use speech recognition, machine translation, every time you use your credit card in the form of fraud detection, and a variety of other applications have machine learning at their core. Okay, so to do that, the field provides a variety of capabilities. So in some sense, it's really a confederation of capabilities is what machine learning provides. And so each of the bullet points that you see on here is a great. So each of the bullet points that you see on here refers to a class of data analysis problems, right? So if you can fit your problem into one of these classes, then there will be one or generally several or a large number of algorithms that can be applied to your problem. So for example, in the case of classification, which I'll be talking more about, if you can frame your problem as one of mapping some entities to discrete labels, for example, mapping emails to the labels spam or not spam, then you can apply any of a number of different classification procedures to derive decision rules for making those kinds of predictions. If your problem involves predicting real numbers, then it's a regression problem, and of course, there are a whole variety of others. So it can take easily a semester to introduce all of these. It can take years to become conversant in all of these, and so we only have an hour or 2 hours in aggregate, and so we'll be talking about just two today, in particular classification and clustering. So these are two of the, I would say, most widely or commonly occurring, and as a result, often the most useful classes of problems. So I'll spend the next roughly hour, or at this point 50 minutes, talking about classification. Tamara, after the break, then will come up and talk to you about clustering. And our focus today is going to be on implementability and scalability. Okay, so rather than giving you some high-level overview where I throw out the names of many different algorithms and explain very high-level concepts, I will give you some intuition, but we'll also try to leave you at the end of today in a position where you can implement at least one clustering algorithm and at least one classification algorithm on Spark on large amounts of data and actually gain practically reasonable performance. Okay, so as a result of that, we're really only going to scratch the surface of these topics. And I'll be focusing on relatively simple algorithms, but they are actually widely used principally because they are scalable and easily implemented. Okay. Okay. So before I dive into that, before I dive into classification, let's just look at what a typical data analysis workflow might look like, or typically does look like. So unsurprisingly, you start by getting your data into your processing infrastructure of choice. So today, and hopefully after you leave here today, that will be Spark. Then you'll typically do some sort of data exploration. So that involves, looking at the raw data, maybe plotting it in some different ways, slicing it up a little bit. So you might be doing that at the Spark shell or using Hive potentially, or Shark. After that, you will typically pre-process and featurize the data. So pre-processing might involve, for example, eliminating bad or deformed records. Featurization is the process of preparing the records in your data set and transforming them into a form in which they can be fed to a machine learning algorithm. So typically that involves basically taking your data, you have some set of data points, and basically deriving numeric descriptions of them. Most machine learning algorithms expect the data that they're being presented with to be in a numeric form. I'll talk more about this process. So this is where we're going to basically begin our story in this talk. So typically after you've featurized your data, you'll feed it to some machine learning algorithm, and that might be, for example, a classifier or a clustering algorithm that will then take the data and build some sort of model. And then finally, after you've obtained your model, you'll do some sort of evaluation, right? You obtain some predictor, for example, a spam classifier. You'd like to answer the question, how good is that predictor? Maybe the data was really noisy, and so I didn't get anything useful out of this, and when I try to deploy this thing, it's going to be terrible results, and everybody's going to stop using my email service. That'll be probably a pretty bad outcome, so you need some way of evaluating your classification procedure or whatever machine learning model you've trained. And I just want to point out that I've included double-headed arrows on all of these because this is typically not a strictly linear and unidirectional process. Typically, in addition to just toggling back and forth between steps, you'll often even loop back. For example, you'll reach the evaluation phase, obtain some accuracy number for your model, and then loop back to pre-processing to incorporate whatever insights you've gained into deriving different transformations of your data to improve your performance. Okay, so it very much is an iterative and feedback process. But anyway, so we'll be focusing particularly on this learning phase in talking about how to do it in two different settings, and also discuss how you prepare your data and evaluate. Okay, so first of all, let's start with what is classification. Okay, classification is the process of learning to map from entities to discrete labels. Okay, and we're going to refer to entities as x's and labels as y. So let's just make that concrete. We'll use spam classification for today as a running example. So our entities in this case will be emails. For each of them, we want to give it a label. Is it spam or not? So the way we do this, right, is we collect some label data set. So whenever you use Gmail or whatever email client you use, there is typically a report spam button. So that has, number one, the effect of removing spam emails from your inbox immediately, but number two, of adding them to literally a training data set that these companies are using to train classifiers that are then used to improve or maintain the performance of the spam filter. Okay, so that your label data is typically coming from past, in this case, labeled emails that are human labeled. And the goal, of course, is to use this past historic data to derive some decision rule classifier, which in the future, when you receive a new email, when it comes into your email server, you can use this classifier to predict whether it's spam or not. Okay, and again, our continuing notation for the entities, for the emails in this case, is going to be x's, and the labels spam or not spam will be y's. Okay, so examples of classification, obviously spam filtering, but for example, click-through rate prediction or click prediction, right, lies at the heart of billions of dollars of revenue at Google, sentiment analysis, fraud detection, and others. Okay, so let's make this process a bit more concrete. How do you actually go about preparing your data and training a classifier? So we start with some labeled data points, some number of data, which are in the form of pairs. Again, x's and y's, emails and labels. The first step is going to be to randomly split your data into two parts. Okay, and it's important that these parts be disjoint. They need to be independent. And in particular, the first is going to be a larger training set, for example, 75% of your data. The second part will be what we'll call a test set, which is a much smaller fraction of your data, say 25%. Okay, once you've done that, you're going to take these two different data sets and pre-process and featurize them. As I said, featurizing is of particular importance, and it is the process of taking your raw data, for example, emails, and turning them into numeric descriptions of that data, which we would call feature vectors. So you're going to take an email and turn it into a list of numbers that somehow encapsulate the salient information in that email that's going to be used for the classification process. Okay, so then after we featurize, we're going to take the training set, this larger set of data, and we're going to use only that to train a classifier. So that's the process of applying some machine learning algorithm and outcome, some decision rule that we can use in the future. As I said, we then want to evaluate the classifier, and this is exactly why we split our data into two parts. We evaluate the classifier on this independent test set, I'll go into more detail about why we need to use independent sets of data to do this a bit later, but basically this avoids being overly optimistic when we do our evaluation. Okay? It avoids us reusing our training data for the evaluation, and thus prevents us from being biased when we generate accuracy numbers. Okay, and then the final step is, of course, that once we've done this and then we are satisfied that, that our performance is as good as we would like, hopefully, we can actually use the classifier to predict. Right. Okay, so schematically, it looks like this. We have our full data set. We split it into two parts. We then do this featurization process, which I'll talk more about, but basically it's taking this raw data. It could be emails, it could be images, it could be videos, and essentially turning it into numeric descriptions. We take the training set, we turn that into a classifier. We use the classifier and the test set to generate an accuracy number. And then similarly, once we have done that, we can also use the classifier to take in a new data point, such as an email, and make a prediction, such as whether or not it's spam. Okay. Are there any questions at this point before I go on? Great. Okay. So, spam classification, right? So we'll delve a bit more into this example as sort of a way of keeping things concrete for now. But again, right, you have your emails and you have your labels. So here's an obviously spam email with its label, not spam with the label. Okay, that's literally what your data is going to look like when you get it initially. Okay, so what is featurization, right? As I said, most classifiers, indeed most machine learning procedures, even beyond classification, require that your data come in the form of numeric values. Okay, so most classifiers can't just accept a string and then classify that. You have to do this intermediate step before you feed the data to the classifier of turning it into a feature vector, which is a vector of real numbers. So that's what featurization is. It's this transformation process. Okay, so in some cases it's straightforward. The data is already numeric, obviously, right? It's like patients in a hospital who have blood pressure, height, and so on. But in many cases, you'll have to put in some effort here. Now, that effort is not going to be in vain because this is actually a big opportunity for you, the user, and presumably non-machine learning PhD, to put in your domain knowledge, right? So the classification procedure was written up in a paper somewhere and perhaps even conceivably even implemented by someone else, but the way you get your knowledge into this whole process is by controlling the featurization in many cases. So by determining, for example, which tests you do on a patient and how you encode those values in numbers, or how you turn emails into numbers, or how you turn images into numbers, that's how a great deal of how you'll add your own knowledge of what's going on in the data. Okay, so for example, in the case of text, how might we go about generating these feature vectors from strings, right? So what we typically do is use something called a bag of words featurization. And in this case, of course, our entities are documents or strings. So the first step is we build a vocabulary, which is just build a set, determine the set of unique words that occur in the training set. Right, so that's going to have some number of words. We'll call that V. And for text, that could be tens of thousands to conceivably millions. Right, number of unique contiguous strings that occur in emails is pretty big. And then how do we, once we've done that, that's sort of an aggregate process on the training set, how do we then take a new document and turn that into a feature vector or a list of real numbers? Well, we're going to generate v-dimensional feature vectors, which are going to have one element per word in the vocabulary. Okay, and it's a very simple process to fill in this feature vector. We're going to look at each cell I, which corresponds to some unique particular word in the vocabulary. Okay, and we're just going to put a 1 in that cell if the document we're looking at contains that word, and a 0 otherwise. Okay, so it's going to be a big, long vector of binary values. Most of those values will be 0, right? Because most emails, for example, are not going to contain most of the words in the dictionary. But it's going to have some ones. Okay, and that encodes actually a great deal of the information in the document, if you think about it. What it does not include is information about the ordering of the words, but it turns out for many tasks, that's okay. Okay. So already there, in some sense, we've actually used sort of some element of domain knowledge in saying that, we think for spam classification, we can probably get pretty far without knowing too much about the ordering of the words, but just about which words are in there, right? If an email contains the words, eliminate debt, money, it's maybe more likely to be spam than if it just contained hi, how are you, right? Irrespective of the ordering of the words. Okay, so concretely in our case, right, we construct this vocabulary by taking our emails and just listing out the unique words. Here I've given a reduced list of words. I've also used domain knowledge here, right, by not including words like us, which or which are probably not that informative, and also so that things fit better on the slide. So, okay. So then we take some email, and how do we turn it into a feature vector? Right? We'll just do this lookup of the different values. Right, for the word bin, it doesn't occur in the email, so it gets a 0. The word det gets a 1 because it is in the email. Eliminate gets a 1 because it is in the email, and so on. Right? And so that's how we generate feature vectors. And we just do this for every email in our training set and every email in our test set. Okay, so that's the featurization process for text. Right? Yes?
Whatever have two similar words in a sentence, would it be true or would you have one?
Yeah, great. So that you would have to control, right? So, yes, sorry. So the question was, what if you have two similar words in your sentence or in your document? Do they get two different cells in this feature vector, or can they be the same cell? And the answer is, well, if you have some good way of realizing that they're similar, then you can put them in the same well by basically doing a pre-processing stage before the featurization, where you look at every word and sort of map it to a common stem, for example. Right? And then you do the bag of words featurization. That will automatically map words that were mapped to a common stem into the same cell. Does that answer the question? So you need...
What if they're exactly the same?
Oh, if they're exactly the same,
yeah,
then yes.
Let's say we have two depths there. We will have 2 in the vector. We will have still 1.
Yeah, so either way will work. You can actually use either one.
Okay, thanks.
Yeah. Okay. Other questions? Okay, great. So we've done this featurization process. Now our data is in a form where it can be fed to pretty much most classification algorithms that exist. Once you've done this bag of words featurization, you should be able to feed your data to those algorithms. So now let's discuss an algorithm that you can actually go home and implement. So how do we go about constructing a classifier? Well, one way is to build a probabilistic model, which is to say, take the training data and build a model that tells us essentially what typical data looks like. So it's going to tell us the likelihood of observing any particular XY pair, namely any particular email text, comma, label pair. Okay? And remember that X, again, is the feature vector for the email, Y is the label. Okay, so this is going to be a probabilistic model that assigns a number to any such pair, telling us how typical is that pair. High numbers, high probabilities will say it's pretty typical. How do we predict given such a model? Well, we're going to take our email, and remember we don't have a label for this new email, right? We just have this feature vector X. Okay, and we're going to compute two values. We're going to compute the likelihood assigned by the model to the pair X spam, and the likelihood assigned by the model to the pair X not spam. Okay, this is going to give us two numbers, and we're going to choose the class that gives the higher value, right? And hopefully this is intuitive, right? And the idea is that you want to choose the class which our trained model gives the highest probability to, right? Okay. Yes? I can repeat the questions. It's fine.
So you're asserting that spam and not spam are not complementary here.
I'm sorry, what do you mean by that?
I mean, are those probabilities complementary?
Yeah. No, in this case, because of the particular form that I'm using here. But yeah, if you had done a slightly different calculation, which would give the same classification, same classification results, yeah, basically the assertion is that the model is assuming that they are mutually exclusive. Indeed. The way I've expressed it here gives you an easier way of calculating which class to predict, but doesn't make that explicitly obvious. Okay? Okay. But the intuition hopefully still holds, that essentially you want to choose the label that your model is giving, sort of saying has the highest probability of being associated with this email text. Okay. Okay, so then the question simply becomes, what is a reasonable probabilistic model which will allow us to generate these likelihoods, which in turn will allow us to generate predictions for class labels? Okay, so let's start with the simplest possible model we could. And this is going to be a model which basically ignores the content of the email and just sort of uses some global prior notion of how likely spam is. Okay, so can we say anything about the likelihood of an email being spam before we even see the email? Right. Okay. This would in some sense be the most basic way of generating predictions. Right? We don't even have to worry about the words in the email. We just generate some kind of crude prediction. Okay? The answer is yes, right? We can just sort of generate a global probability of spam by just looking at the fraction of training emails which are spam, and then gives us an estimate sort of the general likelihood of an email being spam. Right? And this makes sense because if magically spam were extremely unlikely, we should probably in general be pretty biased toward not predicting spam for an email. Right? So this seems like a reasonable starting place. And of course, this is encoding the fact that they are indeed complementary, right? It's the fact that the global probability of an email not being spam is exactly 1 minus the probability of it being spam. Okay, great. So we're going to call this quantity, which we'll write as P of y, where y is either is the label, spam or not. We're going to call this the class prior, right? And prior is in there, again, because these are probabilities computed prior to seeing the content of any email. Okay, it's just based on the class labels. And of course, if you were to use this actually as a classifier, right, for any new email, you wouldn't even look at its content, and you would just predict its label based on whether spam or not spam were most common in the training set. Right? And that would be a classifier, indeed, but it would be like an extremely crude one. Right? And we could tell you what its accuracy would be. Its accuracy would be roughly the probability of the most common class. Okay. Now that's obviously, I hope, unsatisfying to you, because we probably should be using the content of the emails to adjust our predictions. And so then the question becomes, how do we take this baseline and adjust its predictions using the content of the email? Okay, so let's say, suppose that we knew an email were spam. So suppose that we have some email and we know it's spam. Then let's try to just say, attack the easier problem of not characterizing email in general, but just trying to characterize spam emails. Can we build a model that sort of characterizes what the typical spam email looks like? Okay? And of course, similarly, we'll also seek to build a model that characterizes what the typical non-spam email looks like. And then at the end, we'll put all of that together. But how do we go about actually even building a model for spam emails? Okay, so as an example, so we have some email, in this case a spam email, eliminate your debt by giving us your money. I've given its feature vector here, right? Remember that each of these vector elements corresponds to some unique word in the vocabulary. 0 indicates that that word does not occur. 1 indicates that it occurs. And again, we're eliminating ordering of the words in the email here. So the probability of seeing an email with this feature vector in words is this, right? So this isn't extremely readable, but just actually reading it, right? Basically, the probability of seeing this email is the probability of seeing the word debt, and seeing the word eliminate, and seeing the word giving, and seeing the word money, and not seeing any other of the vocabulary words. And we want this probability conditioned on the assumption that this email is a spam email, because we're working to build a model of the typical spam email. So, right, we just want a probability, assuming the email is spam, what's the probability of seeing an email with this content? Great. Writing that using the feature vector notation rather than in words, it becomes much more compact. Right? What's the probability of seeing exactly this feature vector under the assumption that the email is spam? Okay. So what we want to do is be able to generate probabilities of this form. What do the feature vectors of typical spam emails look like, basically? Okay, the problem here, so one way of doing this might be to say, okay, well, let's just look at our training set, and we'll just count up the fraction of spam emails which have feature vectors that look exactly like this. Right, and that's going to tell us something about how likely this feature vector is to occur. The problem is that we're unlikely to see many identical emails. Right? We might see spam emails which have eliminate, debt, and money, but not the word giving. Right? But that should still probably give us some information about how likely it is to see emails that look like this without the word giving. But sort of treating these feature vectors completely independently in this sort of all glommed together form doesn't give us that kind of generalizability. Okay, so how can we get around that? Well, we simplify. We actually divide and conquer. So what we're going to do is actually just model each word in the vocabulary independently. So before we were modeling whole sets of words all at the same time. Okay, and now instead we're going to just build independent models for all the different words in the vocabulary and then put them all together. Okay, so we're going to assume in particular that the probability of seeing a given word, such as eliminate, is independent of the probability of seeing any other words, such as money. Right? So let's say we're talking about spam emails. So we're going to say, given that we're going to be looking at a spam email, There's some probability of seeing the word eliminate. There's some different probability of seeing the word money simultaneously or independently, and those are just not related, right? Now, in some cases, that may be a better assumption than in other cases, but generally it turns out as a practical matter to be pretty reasonable with respect to modeling performance. The key thing is that it yields a crucial simplification of the model and hence of the computation that you need to do. Okay, so as a result of this, the probability of an email becomes this form, right? It becomes a product of these individual word level models, in contrast to what we had before, which was this sort of, big probability of an entire set of words simultaneously. Okay, that's what this was. This is just probabilities of individual words independently. And then we put them together using this multiplicative form. Okay. Why is this a good thing? Well, as you might imagine, right, it's much easier to estimate and form a model like this than it is to form a much more complex model of entire sets of words. Okay, so the key is that we only need to model the probability of seeing or not seeing any particular word. Okay, and this turns out to be easy, right? The reason it's easy is that to estimate one of these probabilities, again, this is the probability of, for example, an email with label Y, such as a spam email. The probability that a spam email contains word I is simply estimated by looking at the fraction of emails in the training set which have label Y and which contain the word I. Okay? Questions? Yes? I'm sorry, can you repeat that?
So in order to compute the individual probability of a word given spam,
Yes.
you're counting the frequency of that particular word appearing in all the spams.
Yep.
So instead of doing this individual counting, you can do the feature vector counting across the spam.
Right, so you can do that. The problem is that they're going to be, yes, repeating the question, sorry. So the question was, instead of doing these counts for individual words, can you perhaps just generate counts for entire feature vectors occurring among the spam emails? Is that the question? Right, and the answer is, as I said, or as I alluded to at least, the difficulty there is that there are a huge number of different feature vectors in the training set. You're going to have, if you have 8 different words, right, there are, a very large number of different possible feature vectors that can be formed using 8 different words. And typically, well, maybe not that many with 8, but if you had 1 million different words, right, that's a huge number of different possible feature vectors. And so typically, you won't have feature vectors repeating very much in the training set. You'll have a huge diversity of feature vectors. And so, the count for any one of those might be 1 or 2, right? And so you can't generate reliable fractions typically for entire feature vectors. You can generate reliable fractions and estimates for individual words because an individual word is going to occur in some potentially large fraction of spam emails. Yes?
Hello? Yeah. So if I understand correctly, you're saying that due to the feature vector dimension space, you're unlikely to get enough sample to calculate the
for any particular value of the feature vector.
Yeah, is that the opportunity in big data that you can do that?
Yes, so in fact it turns out, so there is an opportunity there. Okay, so one caveat is that often big data refers to, at the very least, the number of data points is increasing. Yeah. But typically the problem is that as the number of data points increases, typically also the number of features increases. So in the case of email or text, as you see more and more documents, typically also the number of unique words that you're seeing also increases, right? And that makes sense. As you read more books, you learn more words, right? So that's one issue. So the dimensionality is increasing with the number of data points typically. On the flip side of that is that indeed, yes, you do get more leverage as the number of data points increases, and but not enough to do typically not enough to do the very direct thing that you're talking about. There are ways of going about sort of comparing feature vectors to each other directly without going through this kind of simplification. Those typically yield more complex algorithms than what we'll be talking about explicitly today. But typically you can't do very direct counting on feature vectors. That still generally remains infeasible.
I see. Thanks.
Okay, other questions? Okay, so at this point, right, we have the ability to estimate all of the pieces of the model. We can estimate these word level probabilities, which in turn give us a model for what a typical spam or a typical not spam email looks like. Remember, we estimated this P of y, this class prior, that had to do with the global probability of seeing a spam or not spam email. And the key is that the estimation processes for these, right, yield, number one, very compact forms for the model. We only need to maintain individual probabilities for seeing individual words. So if there are 1 million words in our vocabulary, that yields order of 1 million parameters in the model, one per word level model. And furthermore, this training process, right, is highly scalable. Right? We just need to compute essentially basic statistics of the data. And doing that, right, hopefully at this point you're convinced can be done very easily in a MapReduce fashion, with Spark, for example. And furthermore, these can actually be updated very straightforwardly in an online or streaming fashion. So tomorrow you'll see a talk on something called Spark Streaming, which gives you a way of processing big data in a streaming online setting where you're just seeing one email at a time and you can't just store them all in batch. And here you can just update these counts as you see more and more emails very straightforwardly, and the model remains exactly computable in that setting as well. So as promised, highly scalable, and hopefully shortly you'll be convinced of its implementability, or you're already convinced of its implementability. But just to put it all together, right, so we first estimate the class prior, P of y. Again, that's the sort of global prior probability of seeing a spam or not spam email. We also estimate what we would call a conditional probability of seeing any individual word I, given that we know the class label. So essentially this tells us about sort of the typical likelihood of seeing any particular word in a spam email and the typical likelihood of seeing any particular word in a non-spam email. Okay, and the notation we use for that is this, right? So we've been using this so far just to make that explicit. We would read this as the conditional probability of xi equaling 1, given that we have some class label y. Okay? And so finally, we can take these word level probabilities and put them together to form the sort of total conditional probability of an entire email, again, given knowledge of the class label y. And that's simply the product of the conditional word probabilities, as we saw. Okay? So we've divided and conquered to create this P of x given y by reducing it to a product of individual word level probabilities. And we also have this global probability. To put those together, okay, remember we want sort of this entire model, this joint model of the likelihood of seeing an xy pair. Right now we kind of only have individual pieces of this model. We have a model for the y's in isolation. We have a model for x's given y's for what a typical spam or non-spam email looks like. But what we don't have yet is this sort of total model that's actually going to let us fuse all of this information together and make predictions. Yes?
Can you go back to the previous slide? So the multiplication thing that you have in the end, is that because of the Gaussian independence that you assumed?
Because of the, oh yes, it's exactly because of the independence. We assume the independent, yes, sorry. Thank you for the reminder to repeat the question.
Because that's a simplification, I think, assuming of Gaussian independence.
Yeah, wait, so let me repeat the question. The question was, is this multiplicative decomposition a result of our assumption of independence on the feature level, given the class labels? The answer was yes, and indeed that is absolutely a simplification, one which technically is not necessarily strictly merited by the nature of the data, but which does typically or does often yield very reasonable models. Okay, and in fact, that simplification yields both greater efficiency in the modeling standpoint. We have many fewer parameters this way, but also computationally. Okay.
And second thing I had is like,
Yes.
we want to predict the label, right? And until now, we have all of our, like, the model that we're trying to build is assuming that we already know the
Yep.
label, what would be the problem.
We're about to get there.
Flip it or something?
Sorry?
You want to flip it or something?
So the question was, we want to, right now we're assuming we know, well, this part of the model assumes we know the label because we're conditioning on it, but we'd like to somehow, incorporate something about the label not being fixed in the model. And the answer is we're going to do that in the next slide or two. Okay. So remember, we want this joint model, and that was exactly the question. How do we sort of put the model for the y's together with the model for the x's given the y's? And so the key is that the probability of observing any particular pair can be decomposed, okay, intuitively as the probability of first observing a label. For example, if we were generating an email, we could say, okay, first we're going to say it's spam or not. Right? We just generate that label, and then given the label, we're going to say, okay, well, what's the content of that email? What does a typical spam email look like? And there you go. There are the words in the spam email. Okay, so this is exactly what this notation expresses. It says that this sort of joint, that this joint model for pairs of emails and labels is equal to the product of the label model times the email model, essentially. So it puts those two pieces together, okay? And this is just a fact about conditional probabilities. It's just fundamental fact. As an example, right, so it would look exactly like this if we just substitute in values for x and y. Okay. So how do we use this again to predict a label for a new email? Okay, the way we're going to do this is basically what I said earlier. We're going to compute two quantities, the probability of the email's feature vector x and the label spam. We're also going to compute the probability of x and not spam. Remember, we don't have the label at this point. We just have the x vector. We want to predict the label. So we compute these two quantities. We actually compute the logs of the probabilities. I'll tell you why in a minute. And then we just choose the label which gives the higher of these two values. Okay, the reason we put in the logs, and this is actually an extremely important practical point, if you were to implement this and you didn't use these logs, your implementation would most likely fail. Okay? The reason is to avoid a numerical issue. It's to avoid underflow, which would otherwise occur when you compute this conditional probability p of x given y. Okay, and the reason is that the p of x given y is the product of many small numbers. Products of numbers less than 1 degrade or go towards 0 quite quickly, exponentially quickly, and so you'll end up with underflow if you don't work in the log domain. To write this out explicitly, right, we have this p of x and y. These are the numbers. The left-hand side is what we're trying to compute to make predictions. Remember, p of x and y is equal to p of y times p of x given y. Okay? The p of x given y decomposes into word-level probabilities here, still times the p of y. And the key now is that the log splits this product up into a sum. And it's a sum of these logs. Okay? And these logs are now just sort of well-conditioned numbers. The sum of them is all well-conditioned and everything is okay. If you try to first compute this product inside of the log, okay, you would get an underflow, and nothing useful would happen in most cases. Okay, so you, in general, want to compute these quantities directly via this sum. Okay. Okay, so what you've just seen is an instance of what's called a naive Bayes classifier. Alluding to the gentleman's question, it's called naive Bayes exactly because it makes this, no, it's called, the Bayes is in there because it's a probabilistic model. Naive is in there because of this independence assumption on the feature level. Okay, despite the name, it actually turns out this is still fairly commonly used. In fact, it has in fact been used to implement spam classifiers, although the state of the art is now in that area is beyond that. But it is still commonly used in many cases because of its simplicity and because of its scalability, and it does often give reasonable results. It applies exactly as I've shown it to you to any classification problem where the feature vectors you're generating are binary valued. Right? So it doesn't actually have to be text. It could be something else. It could be, for example, data about patients where you have binary valued observations of some sort. Is their height above 6 feet or below 6 feet would be an example of that. Granted, patients may not be the best example there, but there are a variety of cases you can imagine where binary values would come up. But the question becomes, well, there are many cases where we have real valued features, such as actually more naturally in the patient example. How can we deal with this case? Okay, so we can actually still use a naive Bayes classifier with a slight modification, but not a fundamental one. So we're still going to model each element of the feature vector independently. We're going to keep that because, again, it simplifies our modeling, it simplifies our computation. But the key is, what's going to let us accommodate real values is we're just going to change the form of these individual feature level models. Okay, and this is actually a source of great flexibility for naive Bayes, right, in that whatever feature value data you have, you can just choose an appropriate model here, and now you can use naive Bayes on that data. Right? So you can actually even have feature vectors which include some binary valued elements and some real valued elements and apply naive Bayes. But just to tell you concretely how to handle real numbers, so again, we need to specify a form for this conditional. Okay, so if xi, instead of being a 0 or a 1, could be 5.3 or 7.9 or 1,000,003, right? How can we model this? Well, we can just make it Gaussian. Okay, so the form for this would be, okay, so if we make P of xi given y Gaussian, which is often a very widely used and fine generic choice in the case of real valued data, okay, it's going to look like this. So given parameters mu and sigma, these are the mean and the variance of the Gaussian, you compute the probability of a given xi value, such as 5.3, by simply plugging into this formula. Okay, and this formula basically expresses what you would graphically would be essentially a bell curve, right? And the mean is simply where most of this distribution is centered, and the variance is kind of the spread of this distribution. So mu is kind of the typical expected value of the xi's, and sigma is, how variable are they? Okay. Notice that I've put two subscripts on the mu's and the sigmas, and the reason is that, again, remember we have different models for different features as well as for different classes. So for example, if I am trying to classify, if I have people and among their features are height and blood pressure, and I want to predict their occupation as being computer scientists or basketball players. Okay, so if the feature is, say, height, right, first of all, for different values of y, for basketball players and computer scientists, I expect the mean height of computer scientists to be different from the mean height of basketball players. Furthermore, across different features, right, I expect the mean of height to be different than the mean of blood pressure. Right? So we're going to have different parameters and hence different models for the different feature class combinations. To do the estimation here, we're no longer computing fractions because we have real values, right? It doesn't really make any sense to say, how many times does 5.3 occur in the data set? In general, 5.3, that exact number will occur only once. Right, so we need the Gaussian distribution here gives us exactly a way of generalizing across these continuous values, which are never exactly the same as each other, or typically not exactly the same, but some are, but maybe concentrated in some region. So to do the estimation here, we simply compute the mean and the variance, the necessary parameters, for a given feature class combination in the training set. Okay, so we just look at the training set, we look at the basketball players in the training set, and we say, what is the mean of their heights? What is the variance of their heights? And those become our parameters for the basketball player height model. Similarly, we can do the same thing with blood pressure for basketball players and so on. Okay, and if we knew more about our real valued data, if we knew that it were, for example, non-negative, or if we knew that it lay in the unit interval between 0 and 1, we could use other non-Gaussian distributions to incorporate even more of our prior knowledge in the model. I'm going to move off of naive Bayes momentarily, but the benefits here are, so as I said, you can handle different data types, right, by just simply plugging in different distributions for these feature level models, the P of xi given y's. You can also very easily handle more than two classes, right? It doesn't have to be just spam or non-spam or basketball player, computer scientist. It could be basketball player, computer scientist, financier, right? And now you're just computing fractions still as before. You just have to train more feature level models. Hopefully you're convinced it's simple and easy to implement. It's, I hope, very clearly scalable. Which is, of course, these are all the reasons, essentially, we chose to go in particular depth in naive Bayes, so that you can hopefully, at this point, implement it on Spark if the need arose. Of course, it does have shortcomings. The name naive is in there not for nothing. So first of all, this isn't at the bleeding edge, and in fact, this will not be as accurate in general as more sophisticated state-of-the-art methods, but it will generally give reasonable results. State-of-the-art methods, on the other hand, unless you're using an existing implementation or you hire a machine learning expert, or are working with a machine learning expert, or are a machine learning expert, it's going to be a little difficult to implement those, okay, at least reliably, in many cases. So as we noted, this independence assumption, right, on the feature vector elements is one limitation. You can actually get around that pretty straightforwardly if you're willing to build richer models of the entities themselves. Right, so you can actually just model these P of x given y's, for example, emails given spam, without the independence assumption, for example, taking into account sequence of words in the email. Okay, but now at that point you run into the limitation or the issue that it can be cumbersome to specify these much richer models. It can be actually difficult, they have big parameterizations, are difficult to estimate. Okay, so we'd like a way around that. And in particular, the real difficulty here, okay, is the requirement that we specify this full model for x's and y's. We need the way I've presented probabilistic modeling as I've presented to you thus far has required you to basically build a model for typical data points. This model needs to tell you what does a typical email look like, and in conjunction with that, what is the typical label associated with it. Okay? And in particular, given that an email is spam, what is its typical content? But that's not really what we're interested in, right? And in fact, this isn't even necessary to do classification. What we really want to know is simply given the content of the email, given that I've observed that this email has these words in it, then what is the probability of it being spam? I don't actually need the ability to say, if I know it's spam, what does a typical email look like? What I need to know is, given that I've seen what's in an email, what is the likelihood that it is spam? Okay, and these are two different things to be able to say. Okay, so in fact, what we would like to do is directly attack this guy. So in fact, it turns out that, okay, well, I'll get to that in a second. So naive Bayes models this full joint probability. As I've just explained, doing that isn't strictly necessary. We'd like to get around that requirement for this kind of unnecessary large amount of modeling. Okay, and the key is that, as I said, you don't need to model this full probability. And in fact, even naive Bayes, which does generate this full probabilistic model, in fact, only uses this conditional probability to make its predictions. Okay, I haven't written the prediction scheme for naive Bayes in terms of this quantity, but it turns out that a simple calculation will show you that, that in fact, this is exactly the quantity that naive Bayes is transforming this into to make its predictions. So if we had some way of getting our hands on this quantity, of estimating this quantity directly, then maybe we could do better or do more, or in fact get closer to the state of the art by sort of freeing ourselves from the shackles of this joint probabilistic modeling. Okay, so this is exactly what logistic regression does. Okay, so in fact, it doesn't model P of y separately from P of x given y to build this typical model of a spam email versus a non-spam email. We're just going to do P of y of x directly. Okay, so to explain this, we'll just assume a two-class setting, spam or not spam, for example. Okay, and we're just going to write down a model for P of y given x. What is the probability, given that I see an email, x, with some given content, what's the probability that it's spam? Directly. None of this P of y, none of this P of x given y. Okay? And the model is going to look like this. Okay? So here x is again our feature vector. B is going to be a parameter vector of the same length as the feature vector. And B transpose x, this quantity, is simply a dot product. So in fact, what's happening here is we are forming this dot product, which is simply a weighted sum of the features. Okay, so we take x. Each element of x, each feature, gives some evidence, right, for whether this email is spam or not, or whether this person is a basketball player or a computer scientist. Okay, so each word in an email, right, whether it's money or debt or hello, is giving some small amount of evidence for which class that email falls in. How do we put all of that evidence together? Naive Bayes gave us one way. This is a different and in some sense more direct way by simply taking those pieces of evidence, attaching weights to them. How useful are they for determining which class you're in for each of the two classes? And then we sum up the weighted evidence. Okay, we take that sum and we pass it through this nonlinear function to generate a probability. Okay, this turns out to be quite liberating. Okay, so in particular, first of all, we didn't have to deal with this, well, what if the data is real valued, what distribution do we use, versus if it's just binary valued, what distribution do we use, versus if it lies on the unit interval. We just featurize the data, build a vector of real numbers, and we feed it to logistic regression. Logistic regression takes features, it builds a model, done. There's no tweaking of the classifier itself. In particular, we don't need to sort of specifically choose these P of xi given y distributions. You can just as easily use binary valued as real valued features here. And the key thing is that we can then improve performance often just by adding new features. And those might even just be derived from the old features. I'll tell you a bit more about that in a moment. But the point is that all you need to do as a user of logistic regression is have the ability to generate feature vectors. Okay? And that gives you a great deal of flexibility. Yes? I'm sorry? Yep, next slide. Sorry, the question was, how do you determine the parameter vector? The answer was, it's on the next slide. Okay, yes. It will. Okay, and so, okay, so yeah. So the question was, we have this form. How do we guarantee that our probabilities all sum to 1? The key is that what I've specified here is the probability that y equals 1 given x. The only requirement here is that for normalization, per the question, is that for a particular value of x, these probabilities for different values of y's sum to 1. So what we need is that p of y equals 1 given x plus p of y equals 0 given x sum to 1. Okay? And that's accomplished easily by only specifying p of y equals 1 given x and then saying p of y equals 0 given x equals 1 minus this. That's exactly how it's done.
So you're saying that when you try to train that vector b, you add this additional constraint?
It's not a constraint, but it is basically explicitly kind of in there by virtue of the way we've written down the model. Basically, when you train this thing, you're going to have some training data with y equal 1, some with y equals 0. For the ones with y equal 1, you'll have exactly this term up here. And for the ones with y equals 0, you'll have exactly 1 minus this term up here. And that will enforce that normalization.
Yeah, if my y label is not binary, it's 3.
If it's 3, then you need a slightly different form, but it is possible to generalize this. But this is for the binary form, binary label form. Yes?
Why don't you have a constant term in the exponent so that you can shift, offset
Yeah,
the...
great question. So you could easily put that in there. Another way of encoding that would just be to put in, oh, did I repeat the question? No. Okay. It's really tricky to remember that. Okay, so the question was, why don't you have, or why don't I have, a constant term in here so that you can, for example, enable an offset or a shifting of these values? I could have put it in there explicitly. Another way of answering your question is to say, it's in there implicitly in that I could just add on a constant feature to all of my feature vectors, and that would put in a constant offset, which is actually in some sense another demonstration of the power you have in just the featurization. Right? So, other questions? Okay, so I was asked the question, yep, how do you, right, so I was asked the question, how do you actually get your hands on this feature, on this parameter vector b? The answer is that, we have to get past this slide, and the answer is that yes, this can be trained efficiently. By trained, we mean how do you obtain the parameter vector? You can train it efficiently at large scale, but it's not as easy to implement as naive Bayes. So it's trained by something called maximum likelihood. We're short on time, so never mind exactly what that means, but the point is that this requires the use of an iterative numerical optimization procedure, okay, which requires multiple passes through the data. In its most basic form, this looks like gradient descent. Typically, gradient descent can have relatively slow convergence, and you're going to want to use something more advanced than that. As a result of all of this, implementing this reliably, effectively, at large scale is non-trivial, and we don't have time for it today to go explicitly through it. Okay, which is why I started with naive Bayes. And as I said, this can be generalized to multiple classes. So I just want to mention, we're not going to have time to go through all of these, but we've really only scratched the surface of even just classification. There are a variety of other more advanced techniques, support vector machines, kernelized versions of things, decision trees, boosted decision trees, and so on. These can yield, so a number of these are state of the art. They can yield better performance than naive Bayes. A number of these are quite scalable, but implementing them and also understanding them is, well, the very implementing them is more involved. So we're not going to go into detail today. Nice book by Hasty, Tipshrani, and Friedman talks about all of these. Also, Wikipedia articles are generally pretty good for these. A couple final comments about featurization. We're a little low on time. So it gives us the opportunity to do a few things. As I said, incorporate domain knowledge, but also it allows us to overcome some limitations of classifiers. And as a result of these two things, it lets us improve performance by judicious use of our ability to featurize. Okay, so to incorporate domain knowledge, as an example in spam classification, if we thought sender were important, we could just add features that are based on the sender's email address, right? So we can take our bag of words features, add on sender features, and great, we're probably going to be doing better because we're incorporating information about the senders, okay? But how can we overcome classifier limitations? Okay, so a key thing here is that, as we said, naive Bayes models features independently of each other, okay? And logistic regression actually suffers from a somewhat from a related issue, namely that it doesn't model multiplicative interactions between features. Remember, these models are forming weighted sums of evidence. Okay, but what if what matters is the presence of pairs of words? What matters is that eliminate and det both appear in an email, okay, but either one appearing individually isn't particularly meaningful. Okay, naive Bayes, as you hopefully suspect, okay, since it does this independent feature-wise modeling, doesn't let you sort of capture this kind of interaction term, okay? So one option to get around this issue is to use a different model. Decision trees, for example, can capture these sorts of interactions. But it's more difficult to implement decision trees, so another way around this is to add features which explicitly encode these sorts of interactions. So in this case, you could add features which are simply products of all pairs of bag of words features, right? So now, for example, if we're using bags of words and eliminate and det matter, we're going to have a feature that's 1 if and only if eliminate and det both appear in the email and 0 otherwise. Okay, so this is going to increase the number of features, but now we just take this expanded feature vector and just plug it into our classifier, and we get a new model that may well perform better. Okay, we can also do nonlinear effects in this matter, and if you've heard of kernel methods or you encounter them in the future, this is exactly what kernel methods do implicitly, essentially. Okay. So we started a couple minutes late, so I'm going to take a couple of extra minutes to cover the last really important 2 slides, or 3 slides, quickly, which are on evaluation. Okay, so at this point we've gone through how to featureize, we've talked quite a bit about that, we've talked quite a bit about how to build a classifier. Hopefully at this point you have the ability to do both of those things, or will have the ability to do both of those things on data. The final step is you get your classifier. Is it any good? Did this naive Bayes thing do something horrible? Is it too naive for what I'm doing? Maybe the data was just too noisy. Maybe no classifier would do well. Maybe I need to compare 2 different classifiers. In any case, the point is it's crucial that you have the ability to evaluate your models after you've trained them. Okay, so in this whole set of steps to do classification, I now want to talk about why we held out this, or how we're going to use this smaller test set that we held out. And in particular, we're going to use it to do this evaluation of the classifier. Okay, so again, going back to the schematic, we're going to focus on this piece, which is getting the accuracy after we've trained the classifier, and we do that in conjunction with the test set. Okay, so the question, how do we determine the quality of a trained classifier? There are actually quite a few metrics for quality. Probably the most common, and in many cases a very informative one, is accuracy, okay, which amounts to determining the probability that a trained classifier will correctly classify a new entity that we expose to it. So we took 1 million emails with labels and we trained our classifier. Great. Now when a new email comes into our system, we're going to give it a label, spam or not. If it turns out we're predicting spam, like almost all the time, or in a variety of cases when we shouldn't be, that's probably pretty bad and you don't want to deploy your classifier, right? So we want sort of the probability that we're going to make an error. So how do we compute that probability? As I said earlier, and I want to emphasize this again, you cannot simply evaluate a classifier on the same data that you used to train it, because this will be overly optimistic. This will bias your accuracy numbers. Okay? It is, you see people do this sometimes. It's no good. And the reason, of course, is, for example, consider a kind of trivial classifier that just memorizes the training data. Okay? And when a new data point comes in, says, is this point identical to a training data point? If yes, give the training label. If it's not identical to a training point, then just give the label 0 or not spam, or just spam. You know, just give some generic label. Right? Obviously, it's going to do incredibly well if you test it on the training set, because it just memorized the training data. But if you test it on a test set, it's not going to do well at all. Okay. And this sort of issue plagues pretty much any classifier you might train, even one that isn't quite that trivial. So this is why we set aside a disjoint test set. And so concretely, how do we evaluate accuracy? We train our classifier in the training set without exposing the test set to the algorithm. Then after that, we ignore the known labels of the points in the test set, and we use the trained classifier to generate predictions on those points. Okay, so we take just the feature vectors in the test set, we generate predicted labels, Okay? So now for each point in the test set, we have a predicted label and a true known label. And then finally, we compute the fraction of predicted labels, which are identical to the test set's known labels. Great. And that's exactly our accuracy number, or at least our estimated accuracy number. Okay? And one thought you may be having now is, well, okay, this is great. It lets us evaluate the accuracy of our models, but it seems kind of inefficient. We kind of had to not use 25% of our data when we were training. Wouldn't it be great if we could train on more data, right, and still get some number for accuracy, some way of evaluating our accuracy? Turns out the answer is we can do that. There are more sophisticated evaluation methods, cross-validation being an example, which allows more efficient use of data. But nonetheless, this sort of holdout test set that I've been presenting to you so far during this talk still provides a perfectly reasonable way of doing it. Okay, that's it for classification for today. I'm happy to take any more questions, although we are, it seems, in general, running a bit behind. But after this, Tamara will come up and talk to you about clustering.